In this video, I'm going to explore the concept of sensitivity in sound measuring sensors, a microphone in the air and the hydrophone in the water. Both sensors detect sound, but the key idea is how their sensitivity is designed and measured. Let's dive into this concept, but first, we need to understand what is sound and decibel. I introduced in more details in another video, but I give a brief overview here. Sound is a pressure wave, as shown here by a sine wave. Air or water particles are closely packed in the crest area of this wave. This region is the region of high pressure. In the trough, particles are spread apart, a region of low pressure. These alternating compression and refractions form sound waves. The, from the sound wave that travels through the medium. If we do measurements of the pressure, which we hear or we measure, there are a wide range, a huge range of sound pressure values from 20 micropascal, which is the onset of hearing threshold, to 200 pascal for the jet aircraft. We see huge range of sound pressures, and for that reason we use a logarithmic unit, so-called decibel. We set a reference pressure of 20 micropascal and call the 0 dB for this pressure level. Every tenfold increase in pressure adds 20 dB, and this can compress millions of pressure values into a simple, for example, range between 0 to 120 dB for the hearing range of human ears. And you can see here the logarithmic formula that help us towards defining the sensor sensitivity. In this formula, the left-hand side unit is dB, right-hand side we have 20 multiplied log 10 quantity of interest, which might be pressure, voltage, or the ratio divided by reference. Therefore, if we select Q to be pressure, the denominator is reference pressure. Let's move towards the definition of sensitivity. But first, imagine a quiet room where two people listen to a faint whisper. The girl immediately notices and looks up. The man doesn't react. Both here they are exposed with the same sound pressure, but their ears respond differently. The girl eardrums produce a stronger signal to the brain. Just like a more sensitive sensor. Therefore, we can say her sensitivity is output response divided by input receive pressure or sound pressure. Higher sensitivity means a larger response for the same input pressure. The same idea applies to microphones and hydrophones. Sensitivity is the output voltage generated per unit of input pressure. And it's mathematically written by sensitivity is equal V output divided P input. Because the range of possible values is large as expressed in previous slide, we express sensitivity in dB rather than raw volts per Pascal. This makes it easier to compare sensors and work with this data. Since we define sensitivity relative to a reference, its unit become dB per volt per 1 micropascal. This means we're comparing a sensor's output to a standard ratio of 1 volt per 1 micropascal. The formula looks like this, and Q here is V divided by P, voltage divided by pressure. The unit of voltage is volt, the unit of pressure is micropascal. It simplifies a decibel version of voltage to pressure sensitivity. Let's try an example. Suppose a microphone produces 1 millivolt for a 1 micropascal sound. We know sensitivity is voltage in volts divided by pressure in micropascal. Therefore, it becomes this value. Then using the formula for the decibel, we get minus 60 decibel relative 1 volt per micropascal. In general, more negative values mean the sensor is less sensitive, while less negative values indicate higher sensitivity. This final slide shows typical sensitivity for real devices. Hydrophones used underwater often have sensitivities between minus 150 and minus 20 dB relative to 1 volt per micropascal because underwater pressure are extremely small. Microphones used in the air are typically between minus 30 and minus 50 dB relative 1 volt per Pascal. Different environments, same principles. Both measure how much electrical output we get for a given sound pressure input. And that's the essence of sensitivity in acoustic. Thanks.